So, you know, the derivative, right? And the derivative, if you have a function f of x, the derivative is f prime of x. If you have a function y, sometimes you call it y, here's another notation. Then you call the derivative y prime. Or there's another notation, dy dx. And this is an, but look at this. What I'm teaching you here now is we're talking about the derivative, and I guess I'm sort of in 3.2, but this notation was kind of taught to you actually in 3.1. I didn't mention it, I guess. But the notation is f prime of x, or y prime, or dy dx. There's a fourth one, actually, I never used. I do use these. There's a fourth one called d of y with a little x subscript, I think. Anyway. But you're taking the derivative of a function called y, and you're doing it with respect to the variable x. It's kind of a long sentence I just said, but that is kind of how you read this one here. It's the derivative of y with respect to x. And that's just kind of telling me that x is the variable, is what it's telling me. The derivative of y, the function's called y. You're taking the derivative of y with respect to the variable x. Of course, x is the variable, you might say. Of course, x is the variable. Yeah. The truth is, actually, when you move up into Cal 3, there's really no reason to say this now, but by the time you get to Cal 3, you do deal with functions of more than one variable. So then you might take the derivative of y with respect to the variable x, or maybe it has more than one variable, so you take the derivative of y with respect to t, or you take the derivative of y with respect to z. Or, I mean, you could have more variables, but that's Cal 3. So we'll always be doing the derivative of y with respect to x, but we do change the, we don't always use the letters y and x. We might be talking about the height, and we might have h of t, and we might have t instead of x, so. And you know the definition, the behind-the-scenes definition of what the derivative is. I don't even want to write it. That was 3.1. What was it? Here, I'll write it off camera. Here it is, off camera. What was it? Yeah, the slope of the tangent line, that's the words. And then what was the math? You're right, slope of the tangent line.
F of x subtract delta x.
All right, f of x plus delta x, actually, minus f of x. You had to do this a couple of times on your test Friday. But wait a minute, this is not finished. What else goes with this?
Limit.
The limit as delta x goes to 0.
That's a crucial part of it. Right. That's the derivative. That's the slope of the tangent line. It makes sense. I tried to explain it to you, how it's just a slope, but that change in x is getting smaller and smaller and smaller. So it's the slope at one point. It's the slope of the tangent line. But I'm tired of doing that, okay? After doing that for millions and millions of problems, mathematicians have proven and come up with these awesome shortcuts of how the derivative works. Here's one. So I got some cool shortcut rules for you today in 3.2. Here's one. And look how we talk here. I'm going to talk like this. When I state a rule, the way I'm going to state it is the derivative, okay, one notation of the derivative is the derivative of y with respect to x. So I'm going to leave off the y, and I'm going to put the y right here, and the y is some constant c. So it's the derivative of this constant c with respect to x. This is saying, please do the derivative of this constant c with respect to x. And guess what the derivative of a constant is? Maybe you can guess, maybe you can think about it, maybe you already know. It's 0. The derivative of a constant is 0. Now I can throw these rules up here. I can make a big list of rules here. As I do that, though, I do feel obligated to explain them just a little. But here, let's time out and let's explain something a second. You know, if we really do just have a constant, like y equals a constant, like y equals c, what does that look like? What does that look like? A horizontal line is what that is. It's a horizontal line. Now let me ask you something. This is my function. What's the slope of his tangent line anywhere?
0.
Thank you very much. If I had to draw a tangent line there, right there, what would be his slope? If I had to draw a tangent line right there, what would be his slope? If I had to draw a tangent line, what would be his slope?
0.
Thank you very much. The derivative of a constant is 0. The logic or explanation, the visual logic or explanation is that it's a constant and any tangent line you ever have will have a slope of 0. Remember, the derivative is the slope of the tangent line. You okay? That's a nice explanation. This is a very simple rule. You don't have, I mean, at some point you just memorize this and you go with this and you're not thinking about it all the time, but I don't know if I like, I don't know if you like just rules without a little explanation. Here's another one for you. The derivative of this little guy. This is a little function called x. This is, and his derivative is 1. You can think of that visually. What am I talking about here? I'm talking about the line y equals x. The line y equals x looks like this. No matter where you are, what is the slope of his tangent line? What is the slope of his tangent line? What if I had to put a tangent line on this guy, what would be his slope?
1.
1. I mean, he's just a line with a slope of 1. His tangent line will have a slope of 1. I mean, these are kind of like the trivial cases, the very easy, little boring cases. And I'm explaining them visually. This is the main rule of your life. You ready here? It's called the power rule. I'll call it the power rule. That's what it's called. And it is the derivative of an x to a power n. The derivative of some variable x to a power n. And here's what the answer is every time. You ready? You bring the n down, you multiply it in front, and then you subtract 1 from that n minus 1. That's famous all over the world. Ever since 1684. Do you want to prove? Do you want me to prove that one to you? I can't do that one visually. I don't have a nice visual. Let's just practice it a second. Can you please do the derivative of x squared now that you know this rule?
Sure.
Very good. You bring the 2 down, you subtract 1 from the power, so when you subtract 1, it's x to the first, and you're done. That's called y prime, or that's the derivative of that function. That's a function, and that's his derivative, and it's easy. It's called using the power rule. Is this fun or what? Check this out. Can you do this derivative? X to the 7th. The derivative is called f prime of x. According to the rule, you bring the 7 down, you subtract 1 from the power. Is that awesome or what?
So what's the difference with that and x squared?
No difference. I'm doing the power rule. What am I doing? I'm bringing the power down and I'm subtracting 1 from that power. When I subtracted 1 from that, it's 2 minus 1. It left me a power of 1. When you have a power of 1, you don't usually write it. You never write it. But you bring the power down, you bring the exponent down, you subtract 1 from the exponent. That's the power rule for an x to the n. And there's nothing to it. Calculus, maybe you think calculus gets easy. The problem is we got a lot of rules to learn in chapter 3. These 3 are the easiest kind of rules. Right. I'm going to add another one here. Some people have a hard time reading what I'm writing here. I'm writing derivative rules. This says the derivative of a constant with respect to x is 0. The derivative of x is 1. The derivative of any x to a power is this rule. This is how you handle the power. Here's one. The derivative of a constant, when I write the letter C or K, it's a constant. Maybe I should have, and that means there's no variables, you know, it's a constant. The derivative of C times f of x is this. C times f prime of x. Now, I don't know. You know, this is math. Math is, we have to state the rules. We have to define the rules for you. And some of them you are very logical. You think, why did he write that down? Of course that's true. Well, of course that's true is a little bit of a naive statement. But it is true. A constant times a function. If you're trying to do the derivative of a constant times a function, you just kind of, what this says to me is you kind of slip past the constant and you do the derivative of the function times the constant. Like this. What if I wanted to do the derivative of this? Well, what I'm saying is I would kind of slip past the 8 and I would just go do his derivative. That's what that rule kind of says. A multiplied constant. A multiplied constant. A constant multiplied by a function. You sort of write down the constant and go do the derivative of the function and multiply them together. So you can slip past these multiplied constants. So what's the derivative of the x to the 4th?
4x to the 3rd.
Right. And so what's the answer? In reality, you won't see me actually write it like that. I was trying to illustrate the use of this rule, the use of pulling out the constant, taking the derivative, and then sort of multiplying the constant back. That's what this rule says. In reality, can't I just go 4 times 8 is 32, x to... I mean, yes, in reality, I can go straight there. But I'm sort of holding the 8 out, multiplying the 4 down. I mean, I'm doing this rule, but I'm doing it in my head. I don't have to write it out like that. You guys okay? All right, here's another cool rule. I'm gonna put it right here. The derivative of an f of x plus or minus a g of x. So like if you have 2 functions added or subtracted. Well, this rule says you're allowed to, it might be kind of obvious, but you're allowed to do the derivative of each guy separately. You're allowed to do the derivative of the f of x, I'm going to call that f prime, and then add it or subtract it to the derivative of g prime. You're allowed to do each derivative separately when they're added or subtracted. When functions are added or subtracted, you do each term separately. Hey, that's not true for multiplication. It's not true for multiplication. It's not true for division. For multiplication and division, we got a complicated product rule and quotient rule. It's pretty awesome stuff. Technically, that's up in 3.3, so I'll just hold off until Wednesday, maybe. I mean, I could dive in. I could teach you this whole chapter in 3 seconds. No. I can write down a bunch of damn rules, but we need to stop and practice some of these rules. Listen, this guy and these guys together, that's, I don't know. I mean, I'm calling that sort of forms the basis of a lot of rules. That's the basis of a lot of stuff. And let me show you what I can do now. Now I can do the derivative of this. I don't know. I tried to make up something. I think this might have been on your test Friday.
Yeah, it was.
And on Friday, you were supposed to do the derivative the long way. You were supposed to do this to that. And maybe you did. Maybe you messed up. Maybe you did it right. Anyway, today you ain't got to do it the long way. Today, you can use these cool new rules and do the derivative. You know, the first one that pops in my brain, though, is this, you guys. is that there's three, this is one function, but you can think of it as three separate little functions added to or subtracted. I mean, it's three separate terms. So the first rule that pops into my brain is this guy, that I'm allowed to go do each derivative of each term separately. That's important. And then I'll start employing these rules as I need to. Here I go. So I'm going to do each derivative separately. So here I go. I run into the 8. What's the derivative of an 8?
0.
Thank you very much. It's gone. I run into the 7x and I do his derivative. I don't know. There's a couple ways to think, but it's a 7. It's not hard. But you can think of it a couple ways. Let's see. You can think that you hold the 7 out and you take the derivative of the x. What's the derivative of x? 1. You can think like that. You hold the 7 out because it's a multiplied constant, and you do the derivative of the x, which is 1, and then you're done. 7 times 1 is 7. You could think like this. You're doing a power rule. Watch this. You're doing a power rule. What's 1 times 7?
7.
And then you're left with x to the 0 if you subtract 1. What's x to the 0?
1.
A 1. So that's a 7. So you can actually do a power rule on this. Look, I wrote this down kind of like it's its own rule. And I explained it like it's its own rule. But it's really this. It's a power rule. 1x to the 0. 1x to the 0, which is 1. You got a few different ways you're allowed to think. You can think visually. You can think, dude, that's a line with a slope of 7. What's his derivative?
1.
7. Well,
Oh, 7.
he's a line with a slope of 7. His tangent line will have a slope of 7. His derivative is 7. I mean, that's kind of thinking visually. I try to get a little more mechanical here. I'm a little more following the rules, maybe. You can't think visually. You can mix up how you think. You can think a lot of ways. Anyway, what's this answer?
7.
7. And what about this guy? -8, subtract 1 from the power, bring the 2 down, subtract 1 from the power, 8, -8x. Yeah, there's your answer. There's the derivative. It took 2 seconds. It took 5 minutes with all my talking, but it took 2 seconds in reality. That's how easy it is. I mean, I'm anxious to, yeah. I mean, we needed limits. We did limits. We did a chapter on limits. We need limits in calculus. But in chapter 3, we're done with them for a little while. I mean, they're behind the scenes. The proof of these rules, if you need the proof of these rules, you go do the original limit definition.
So the constant 8, right? The 8, which is the y-intercept, I should call it. What did you do with that?
Okay, you ready?
That by itself.
What was the derivative? I did the derivative of each guy separately.
Right.
And he's asking me, what did I do with the 8? What was the derivative of the 8?
0.
0. I could wrote it down for you, didn't I? But
Yeah.
nobody writes 0 down usually. Right, it's 0. Any other good questions? Were you trying to ask something? You good?
Yeah, I was asking you.
Yeah. You don't need me. She answered it. Cool. Any other good questions? So now you can do this. The derivative is. It's so easy, right? Tell me. Shout it out. The derivative is 15x squared. Sweet. Plus 4x.
-8.
Minus 8. See how cool that is? See how easy it is? This is calculus finally. It's awesome. And by the way, now I'm doing derivatives just for fun, cranking these out, getting real good at the mechanics and the rules, and don't make mistakes. But then sometimes I lose sight of what the hell am I doing? What is this? What is this?
Slope of the tangent.
Oh yeah, thank you. So I'll ask you and remind you, and you can remind yourself occasionally, that what you got here is the derivative, and it's It's the slope of the tangent line. It doesn't look like a slope. You might think, oh, it's a parabola. I mean, you're right. It's its own function. It's its own function. But it's a function that tells me the slope of that function. It's a function that tells me the slope of the tangent line to that function. It's a function that tells me the rate of change of that function. It tells me the instantaneous rate of change of that function. It's this new function that tells me the rate of change or the slope of the original function. It's the derivative, right? And if I wanted to use it, I mean, I'm sort of just cranking through some rules here, but what I really like is doing derivatives for the hell of it, but I kind of like doing them for a reason, like this. Let's put this question up here. Find the equation of the tangent line to that function up above at the point x equals... that was just voice lessons I was working. -2. X equals -2. So anyway, if you want the equation of the tangent line, it seems like you need
The derivative.
well, the slope. And to get the slope, you do a derivative. Right, so guess what? We already did a derivative. The new easy way, right? The new easy way, right? You don't have to do this. Don't do this. All right. So now we got the derivative, which is the slope. So now talk to me, though. I am at a specific point. Some of you didn't catch this on your test Friday. See, you're at a specific point. So you don't really call that the slope. Listen, it is the slope, but it's the slope in general at any x. I want the slope specifically at -2. So what should I do? Plug -2 into the derivative. A lot of you didn't catch this on that last question of the test. Here I am plugging -2 into the derivative to get the actual specific slope.
44.
44. That's my slope. Did I lose you?
That's the slope at -2.
That's true. Look what I got here. This is the slope at any x. Hey, is it a changing slope? If you move from x to x, if you move to different x's, ain't this going to be a different number?
Yeah.
Yeah.
Thank you. This is a constantly changing slope. It's a function. At different x's, it's different numbers. Anyway, I wanted the slope at this point. So you plug in this point and you get the slope at this point, 44. You got something different? Well, let me think. That's a 4 times 15. That's 60 minus 8. If you plug in a... Yeah. Okay, cool. 44. Hey, what else do I need? Okay, now that I got the slope, I'm trying to get the equation of a line.
Need a point.
So now I need a point. To do the point slope formula, I need a point. I got a -2 for x. How do I get y?
Plug in the original.
Oh, anytime you want a y, you plug it into the original function. The original function is y. The derivative is the slope. Right. So let's plug -2. I didn't give you the y. Let's plug -2 into the function to get a y value. That's f of -2. This is f prime of -2, the slope. F of -2 is really fun.
-5.
Really?
Yep.
All right, I'll trust you. Thank you. But I still got to check you.
Yeah.
Yeah, you're right. What'd you say?
-5.
-5. Now you got a point and a slope. Point and a slope, and you can get the equation of this tangent line. You can get the equation of this tangent line. Y minus the y value equals the slope times x minus the x value. You guys with me?
Right. Yeah.
That's a y plus 5 equals 44x plus 88. That is plus, so yeah. Subtract 5, y equals 44x plus 83, I guess. Down here in the corner. That's the answer. That's the equation of the tangent line at this point. That's a cool little problem. It was an easy derivative. The derivatives are easy now. Well, they get worse, but Derivatives are easy now. They're not such a pain in it. They were pain. This was a pain. This old limit thing is a kind of a pain. It's cool for you to understand. It's cool at the beginning to understand. To me, it drives home the idea of slope of a tangent line. I see it. I see slope. Sometimes when I'm doing this work, I forget that this is the slope, but this is the slope of the tangent line, right? You know, sometimes it's fun. I don't think I really want to do this, but it's kind of fun after you do one of these problems to maybe pick up your graphing calculator. And I don't know if I really want you doing it right now, but I'm just suggesting that you could graph that function. And the other thing you could graph is his tangent line. And if you typed them both in on the same graph and got an appropriate window, maybe you could see something interesting. This might be a little tough. By the way, that's a very steep tangent line with a slope of 44. That's a very steep tangent line. Almost looks vertical probably. But it is touching this function at -2. I don't know. It's a cubic function. Anyway, it might look something like this. This is me it's a cubic function. It might look like this. -2 might be about right here. Actually, what was the y value? What was the y value?
-5.
Yeah. So how about right here? -2, -5. You follow me on that? Although I totally made this up. But -2, -5 is my point. And at that point, there is a tangent line. And it looks like this. And it's steep as hell. And it has a slope of 44. That's its equation. And then again, you don't have to do it now, but you could pick up a graphing calculator, type in the function, type in the tangent line, play around with a window to get a good view, but you would see what the work you did. You would see your tangent line touching the function once, like a tangent line is supposed to do, right? And what you have is this slope of the tangent line at this point is 44. You start moving and that slope changes. Look at it. Is it getting less?
Yeah,
I think it's getting less. At some point, maybe it hits a slope of 0. And then I think the slope gets negative. Now, this slope is constantly changing. On a tangent line, the slope is constantly changing. Look, the slope is constantly changing. It's got variables all in it. No matter, depending on what x you're at, you got a different slope. Yes, sir.
Can you kind of go over how did you get that derivative using the shortcut?
Okay,
Right.
15. It's easy.
Okay.
It's this. Bring the n down and subtract. It's a power rule. Everything's a damn power rule in a way. In a way, that's a power rule. I explained that a few minutes ago.
Okay.
This is not. This is just holding the constant in front of the function. This is saying you get to do separate terms.
So can you use any of the rules to figure that out? Or
Well, I sort of used. Okay, so
You use combinations.
I'm using combinations of rules. That's right. It ain't one rule or the other.
Right.
You're right.
Okay.
That's good. Listen, so I started with this guy. See, because the first rule I'm thinking about is this one. This one's real important, but it's so common sense you might not stop and think about it. This one says you're allowed to do the derivative of every term separately. So it's like I'm doing 4 separate derivatives, really. I do that derivative, I do that derivative, I do that derivative, and I do that derivative. But really, it's one derivative. But,
Right.
okay, so now, how do you do that derivative? You hold the 5 out, you bring the 3 down, and it's 3x squared. But the 5 is sitting out front, so it's 3x squared times 5. So it's 15x squared. Now, wait a minute, how did I get the 3x squared? How did I get the 3x squared? X cubed, 3x squared. Is that easy or what?
Right.
Right.
Yeah. So then for the 2, put the 2 out, for the 2, put in the x.
2x to the first. 2x to the first. There's another 2 already out there.
Right.
See, sometimes holding them out gets you in trouble, makes you lose them. Anyway, but he's there. I call it 4x. I go ahead and multiply it. I go ahead and multiply that. 15x squared, 4x Negative 8, and that's 0. The derivative of a constant is 0.
Alright, gotcha.
You know, once you learn these power rules, then you run into these. Watch, there's a bunch of these guys, you guys. Look at this. Here's a function. See, that's a function. And by the way, here's another function. Now, this is awesome right here. This is important and awesome and easy and basic, but important and awesome. But look at these guys. Important and awesome and easy and basic. Listen, these two functions, you can do them now. You've learned the rules, but if you look over here at your rules, you might not think you have. You might not realize you have learned these rules. You might not. Look, you got these rules, but to tell it again, there's really only one rule up here in a way. I mean, these are rules, but there's this path, right? This is the rule. This is the rule in a way. But what this says is this rule says, look at it. It says if you have x to a power, you can do its derivative. Does it say anything about being inside a square root? No. Does it say anything about being down in somebody's denominator? No. It just says if you have x to a power, you can do this damn rule. I'm sorry, it doesn't mean to cuss at you, but it does. Listen, so what about this? Can you make this look? So here's what we often do. We rewrite the functions. Can you make this look like x to a power?
Yeah.
How?
X to the negative 2.
Oh, using algebra skills, you know that this is x to the negative 2. Thank you. Now, does it look like a power rule?
Right.
Okay. So that was called rewriting the function, and now you can do its derivative. You ready? So look how I write. Did I do a derivative from this step to this step? Was that a derivative? No, that was just
Yeah.
rewriting the function.
Right.
And did I call it y? So if I called it y, I didn't do a derivative yet. When I do the derivative, I don't call it y. What do I call it?
Y prime.
I call it y prime. Here I go. I call it y prime, and now I do the derivative. And it's a power rule, and it's easy, and it's fun, but I'm dealing with negative exponents now. What is it?
X.
When you subtract 1, it's negative 2, x to the
Negative 3.
negative 3. When you subtract 1 from the negative 2.
Yeah.
Subtraction might be your death. No. Subtraction might get you. Right, subtraction could be your worst enemy. Calculus is easy. Just got to master the subtraction. Cool. You did it. You did a derivative. Oftentimes we like to rewrite the derivative to make it look a little cleaner or better. But this is it. This is the derivative, but let's rewrite it. Any suggestions?
Y prime equals negative 2
Over x to the third. Right. You can something that has a negative exponent can be moved to the denominator and turned into a pi. That's algebra. The negative 2 stays up top, though. The negative 2 doesn't have an exponent. Right. Classic. Cool problem. Yeah. There we go. There's the derivative. What about this one? Can you write this one? Look at him now. He's a square root. If you look over here, you ain't got no rules for square roots. But what you have is you have this power rule. Do you know how to write square roots as powers?
X to the 1/2.
That's algebra. You learned that in algebra. You can write a square root as x to the 1/2. Now it's a power. And now you can do a power rule on his. Now you can do his derivative. You can't really do it like that. You have to rewrite it, and now you do a power rule. It's awesome. The derivative is 1/2 x. Now you subtract 1. That would be negative 1/2. So what did I do? I rewrite. Again, here it is. I rewrite. Then I did the derivative. I did a derivative right here. And then I'm going to rewrite again. I'm going to clean it up a little bit. What do you think I should do to clean it up? If it's got a negative exponent, you can move it to the denominator. So that x to the negative 1/2 can get moved to the denominator. So it's an x to the
1/2.
positive 1/2. But let me just I could write that, or I could write what is x to the 1/2. It's a square root of x. That's my x to the 1/2 in the denominator. That's my x to the 1/2 in the denominator. Well, I know. I mean, this is old. This is algebra exponent rules about roots and negative exponents and fractional exponents. That's what I'm dealing with here. Fractional exponents are roots or radicals, and negative exponents are these denominator things in the denominator. These. But it's cool, man. They fit the power rule. The power rule works on those dudes, on those weird-looking dudes. Can you do this one? Y equals the 5th root of x to the cubed. You need to rewrite it as a power. How do you rewrite it as a power?
X to the 3/5.
X to the 3/5? It's not upside down? No, it's
No.
not. It's not. Here's what you ought. Maybe somebody told you this before, but the 5th is the root. The 5 is the root. And so I'm going to point to that and call it the root. And the 3 is the exponent or the power. And you need to put the power over the root. And one way to make sure you understand that and remember that, this is old algebra stuff, but I'm reminding you this, and I'm saying maybe you can remember that roots, hey, roots grow down in the ground. So the root goes in the denominator. Is that cool? The root is in the denominator. The roots grow in the ground. How about the power comes from above? So the power is in the numerator.
I like that.
Yeah, that's good. That's good.
Whatever. Because people they flip-flop them. They'll write 5/3, they'll get it wrong, and that's bad. So the roots are in the ground. The power comes from above. If you flip-flop that, you would be saying the power comes, you don't want to say that. That's a sketchy area there.
That could be true.
Well, so I rewrote it now. What's his derivative? His derivative is 3/5 x to the
Negative.
subtract 1. A 3/5 minus 1. You get good at that after a while, but it's negative 2/5. Thank you. We're done. That's a function, and here's his derivative. We're done. We do like to clean up these derivatives. I'm not, I'll leave the 3 in the numerator, the 5's in the denominator, and what about this guy?
The 5th root.
I would move him into the denominator, and he's the 5th root if I wanted to write him as that. I guess I would. I don't really have to write him like that. I could just write him as x to the 2/5.
But the negative 2/5?
Well, there's nothing wrong with that. This is correct. We have a habit of cleaning up our derivatives. So when we're done with this derivative. He's totally done and he's totally correct. But we love algebra so much that we like to do algebra.
Yeah, but
Positive.
where's your negative 2? Your negative.
When it moved to the denominator, see, by the way, right now, it's
I
off to the
understand now.
side. And if it's off to the side, it's kind of in the numerator. And when it moved it to the denominator,
It
it
clicked.
became a positive 2/5. Sure. By the way, I don't know. This process of doing derivatives, we're sitting here, we're cranking them out now, you guys. We're doing derivatives, and that process is called differentiation. So some of this is language that I don't always teach you all the terminology, but it's good to mention it. Doing derivatives, you're differentiating. Please differentiate this function. Please take the derivative of this function. There's a lot of different ways to talk. Okay. Here's a couple more then. The derivative of sine x. I'm just going to tell you what it is. This is a rule. I'm stating a rule without proving it. I'm going to tell you what it is. The derivative of sine x is cosine x. I got a couple more for you. I'm going to hit pause though.